So as I told you, we want to start with an introduction to the principle of balancing. What is this all about? Balancing is a type of compensation technique. In a compensation, the principle of compensation, of additive compensation, is that we reproduce an error that has been generated somewhere in the system and we subtract it from the signal with the error. And then we basically compensate for the error. So if you put this in a figure, it would look like this. You have some kind of signal, we call it XT, and you process it through some kind of system, but the system also gives an error. You just want to have a gain like A times XT at the output, but you get something extra, can be distortion, can be offset, can be of any type. And if we have the possibility somehow to reproduce this error, we could subtract it and then have uh, the amplified or the signal multiplied with a gain factor A. That is what we want, and that is basically what additive compensation is. One way of getting the error, of reproducing the error, is using an equivalent system, and then we talk of balancing. So balancing, first we'll discuss balancing with identical elements. So here, consider we have the signal xt, but we can also have the inverse of this signal. So minus xt available. And we pass it through a system. And in this case, we will only consider nonlinearity of the system. So the input-output relation of the system will be described by some function fx. And we can see here fx is written as a Taylor expansion of the input signal. There should be everywhere t. I see there's only t in the third power. That should be everywhere, of course. So this is this is the Taylor expansion of a nonlinear function, and let's see now what comes out of the both outputs of these blocks. The upper output gives us yt just by substituting xt in x, and you see it gives us this first output signal. And the lower we have inverted xt, which means that all even components, all even powers, the sign is not affected, but with the odd powers, the sign will be affected. So you can write it down as a O minus A1 times xt, etc., as has been done here. If you subtract both, then you see immediately that all even terms, because they don't have a sign change, will cancel. And it adds, and we add up the odd terms. So that is what we do here. The y is 2 times all the odd terms. And for example, the offset, which is AO, which is a output when there is nothing applied, that is what we call offset, has cancelled. But also all this even the terms like the quadratic term, etc. So this is what balancing with identical element does. We have error protection with an identical system. The even terms cancel, and we have, of course, a reduced error reduction because of matching. If the both systems do not have exactly the same transfer, exactly the same nonlinearity, then some little parts of this even terms will still remain. Instead of doing it this way, we could also use another function in which this minus sign is already incorporated. So that is done in the next sheet here. And then we are speaking of complementary functions, complementary elements. Let's do it. Let's say we put xt in some block fx and xt in some blocks with a transfer gx. And then we add the results. But now we take fx as we did before, but gx we take a function that has minus on all on all even terms. And then we add the result. And here, let's see what we would get. We would get y the same signal here as before. And here we have now minus AO, minus AT. So now we don't need to subtract, but we need to add the two. And if we add the two, then we have again this compensation of this function. So if we add the complementary outputs, then we have it. And if we subtract the equal outputs with an invert signal, then we also have compensated terms. So this is called error reproduction with a complementary system in which Gx can be written as minus f working on minus x. So Gx is called complementary to fx if minus f minus x equal Gx. That is the definition of a complementary function that we will use later. It seems very abstract, but basically this is the way how SPICE deals with P devices and N devices. They are complementary devices and they don't need an extra set of equations. They just need to flip the argument and the result, and then you can use exactly the same equations. So even terms cancel, and error reduction, of course, again, is limited by matching.